Today, let's talk about some of the things that astronomers have to deal with when trying to observe the universe. First thing that you need to recognize is that sight is the only thing that astronomers have to go by. You can't reach out and feel something out there, except for the few astronauts that have stepped on the moon. You can't smell what's out there, except for some astronauts who went to the moon and space. And by the way, the general consensus is that space smells kind of like burnt steak. That's what the astronauts say. You can't hear stuff. It's coming through a vacuum. The only way to observe things is light coming to Earth. That's the only thing that we can use to observe the universe. So if we study some of the properties of light and what light is, then we have a better understanding of not only what the universe is, but how the scientists know this. What you call light, or visible light, is only one type of something called electromagnetic radiation. Electromagnetic radiation is things like infrared, radio, X-ray, ultraviolet. The only difference between these different types of electromagnetic radiation are wavelength or frequency. So if I look here, this little part is what we call visible light. All of this are different types of electromagnetic radiation. We have everything from a little bit lower than red is infrared, literally means below red, microwaves, radio waves, ultraviolet, X-rays, gamma rays. They're all the same thing, they just have different frequency. Your eyes are only tuned to see visible light. We have equipment, materials, technology that can measure these other things, that can detect those, can react to those. Typically above ultraviolet. Ultraviolet, X-rays, gamma rays, that can be harmful radiation to us, but all of it's just radiation. On Earth, we have what's called the atmospheric window. And this simply is talking about the fact that only certain frequencies of light can actually pass through Earth's atmosphere. Here's visible light marked by a rainbow again. So at this wavelength of light, visible light passes through our atmosphere. And you can see that not very much of the ultraviolet and stuff, X-rays, gamma rays, those 100% blocked by our atmosphere. You can see that there's some infrared over here that can be passed through the atmosphere. Let me talk about that. So 100% up top means it's completely blocked. Down at the bottom means it completely passes through. The light can pass through our atmosphere. What's interesting over here is at 15 micrometers, you have our infrared radiation. During the daytime, visible light passes through our atmosphere, heats up the ground, you know this, and at nighttime, the heat from the ground gets re-emitted back into space. Because there's a little bit of a bump right there, not all of the sunlight gets emitted back to space, so it keeps our planet warm. It's like a little blanket. What's responsible is carbon dioxide. Infrared cannot pass through carbon dioxide. So during the day, visible light passes right through the carbon dioxide, but at nighttime, the infrared has trouble getting out. We have dramatically increased the amount of carbon dioxide in our atmosphere, raising this right here so that less of that infrared energy gets back out into space, which is what's warming the planet. That's the main mechanism. So our atmosphere kind of has this little built-in mechanism so that we don't, have a dramatic increase in temperature like Venus. Venus, this got shut off with so much carbon dioxide, so huge amounts of light came through its atmosphere and never got out. On the surface of Venus, you can melt lead. It's that hot. Your pizza would be, well, probably burnt in less than a minute. I think it wouldn't even do the traditional coal-fired stove, where you get really, really hot wood-fired. I think it's too hot for that. There's a huge chunk over here completely open. All of these electromagnetic waves, this electromagnetic radiation, can pass right through the atmosphere with zero problems. Well, not zero, but almost nothing. And those are radio waves. Lucky for us, we can put satellites up into space and communicate back and forth with them over radio waves. We can do it with laser too, but that's really tricky, and you can see it's kind of messy down on the visible end. But radio waves are a perfect way to communicate. The interesting thing is we know that there are things in space that emit at these frequencies. How do we know that if we can't see them in our atmosphere? You can look at the sun in X-rays, but you can't see it from the ground. So what we do is we put instruments above Earth's atmosphere. This is one reason why we have space telescopes. On the left here, you can see that we have the sun, and we'll talk about this. There's little dirty specks on there. Those are called sunspots, and when we talk about star cycles, we'll learn about that. But this is the exact same picture in X-rays. So we can't see this. But what you can see is that with this group of sunspots, there's something going on with X-rays. And then you can look over here and say, yeah, but nothing's going on there. Maybe there were some sunspots previous. Maybe there's some about to happen. There's very clearly some correlation going here. So it allows you to learn more about what you see. The fact of looking at different wavelengths, different frequencies, allows you to see more of the universe, no pun intended, and discover new things. Over here we have different wavelengths. They do them in false colors. You can't see X-rays. They're not yellow. But when NASA's satellite takes a picture in X-rays, they convert it to yellow. That's nice and easy to see. I think the green is ultraviolet, and each color basically, they keep it the same. So when an astronomer looks at it, they see that color and they instantly recognize, oh, this is in the X-ray spectrum or the UV spectrum. And take a look at these areas. You can clearly see in the same place there's something going on a little bit different in each of those. If you look at the green one, there's more at the top than at the bottom. So this allows you to figure out some of the processes going on. This is where you can analyze it. So looking at different parts of the electromagnetic spectrum is extremely important to astronomers, and putting telescopes up in space is pretty much the only way to do it. There is a telescope, I think it's called SOFIA, and SOFIA, and it's mounted in a jumbo jet, like a passenger plane. So there's actually like a side cut out with the telescope protruding through it, if you can imagine. And they fly really, really high up, higher than the 30,000 feet. I think they go to like 50,000, which is typically where military planes fly. And they get up above more of the atmosphere and the water vapor, and can see a little bit more than other telescopes. So this is cheaper than launching stuff into space, but it's not perfect. But in certain wavelengths, it's basically perfect for what they need to do. the scientists will sit, the astronomers will sit in there at computer screens gathering information and equipment and stuff, and they're wearing heavy coats and gloves and everything because it's cold. They don't really, it's not a passenger plane with all the comforts. It's kind of cool. Sometimes, as I was saying, that they look for specific frequencies, and some frequencies will help a lot better than others. On the right, that picture you see is a famous picture from Hubble called the Pillars of Creation, and we'll learn a lot more about that. But I want to point out something. This little segment right here, anytime you see that, you know it's from Hubble. And there was an astronomer talking to our group once that explained what that was, and I don't remember the details, but there were supposed to be 3 more cameras or 1 more camera that took pictures in that realm, and it was supposed to be a specific wavelength, like, we were looking at the sun. And they decided it was something like $20 million for, it's not just a camera, it's a whole system of stuff. And they decided in the budget cuts that they were just going to cancel that camera and save $25 million. So the astronomer that was talking to us said every time he sees that, he just sees dollar signs and shakes his head. But little distinct thing. Anytime you see that, that's the Hubble. So those pillars right here, believe, are about 12 trillion miles long. It's just dust and hydrogen gas. The nice thing is infrared travels through this the best. So this picture is visible light. That's all you're going to see. But when they take pictures in infrared, they noticed behind this, and I don't know exactly where, I'm just putting a little dot there. They noticed behind it that there was a star that had gone supernova. Supernova, we'll learn about that later, is an exploding star. At some point, now these clouds are so far away, it took a very long time for light to get here. So we are looking at those clouds as they existed, I think 700 years ago, 300 years ago. And the light now hasn't reached Earth yet. I'll get into that in a few minutes. So that star behind it that exploded is close enough that its shock wave would have blasted this dust away. So that picture right there is what we see now, but at the moment is probably gone. But the image of that catastrophe has simply not reached Earth yet. You can see, a lot of X-rays near black holes and other stars. So when we look out at the universe, some astronomers, the ones looking for black holes, will look for X-rays. Those looking to try and analyze the dust and everything will look at infrared. So every astronomer kind of has their specialty. They understand what's going on here. Problems are that visible light, okay, I wrote does not come from very distant objects. It does, but by the time it's here, it is so faint, not even Hubble can detect it. And it gets absorbed and blocked by the dust between stars and galaxies fairly easy. So we don't see a heck of a lot. When we look edge on through the Milky Way galaxy, we can't see the other side. We don't know exactly what's over there. We have bits and pieces of data that tell us, well, this is going on over there in this one spot, and we can kind of fill in the pieces. But if you've ever seen a map of the Milky Way galaxy, that's from 200 years or more of data that's slowly put together to build a picture, and we don't have a full picture. It's kind of got to be filled in here and there. And as I talked about with the atmospheric window, only certain stuff, visible light radio waves, are actually visible from the ground. Another limitation is the huge distances in space. And the first astronomers that really measured it way too short. And they were completely overwhelmed. Hey, you missed that sound. They were completely overwhelmed by the numbers that they got of how big the universe is. And they were wrong by a lot. They way underestimated it. It's kind of neat. Speed of light, how should I put this? It's weird. It's just weird. In the 1800s, they made observations where the speed of light was the exact same no matter how you looked at it. And nobody could figure that out until 1905. Albert Einstein figured that out. That's actually the one he's famous for. So we'll talk about that one later. Light is kind of neat. It travels 300 million meters per second, which comes out to 186,000 miles per second, not miles per hour. That's about 670 million miles an hour. And the weird thing is, there's a lot of weird things about light. Nothing can go faster than light. It's literally the speed limit of the universe. Einstein's famous equation, E equals mc squared, the c is the speed of light. So that's why that says speed limit of c. At this speed, the moon is roughly 200,000 miles away. So it takes about 1 second for light to travel from the moon to Earth. At that speed, at 670 million miles an hour, it takes 8 minutes for sunlight to reach Earth, 5 hours for Pluto. And if you could shine a flashlight from one side of the Milky Way galaxy to the other, that light would take 100,000 years at that speed to cross that distance. That distance is what some early astronomers thought was the entire universe, until they realized there were some things that they had been looking at all along that were not within the Milky Way. They were outside of it. One of them that you can actually see with a really dark sky with the naked eye, it's just barely a smudge, is the Andromeda Galaxy. It's the nearest one. It's huge. The light takes 2.5 million years to get to Earth. So what you see, you are seeing light that is 2.5 million years old. There is no way for us to know what happened after that unless you wait around 2.5 million years. There are galaxies where the light has been traveling for billions of years. So all of this brings us to a measurement that y'all have heard before, but it's really confusing because honestly, the name makes perfect sense if you're measuring this stuff. The distance that light travels in 1 year, which is a lot, is called a light year. So according to this, you would say that the moon is 1 light second away. That's not a time, that's a distance. The sun is 8 light minutes away. The Milky Way is 100,000 light years across. So a light year is pretty massive. And the Andromeda Galaxy is 2.5 million light years away. And there are galaxies that are billions of light years away. So somewhere out there, there's a galaxy that's 65 million light years away. And I like to think that there's an alien there with a telescope watching Earth going, ooh, there's a huge meteorite crashing into it. I wonder if there's anything there. You know, the one that wiped out the dinosaurs. Obviously, that wouldn't work. Telescopes barely show us anything within our own solar system, let alone 65 million years away. They would see our galaxy as a smudge, never knowing that planet Earth existed. Same thing with Andromeda, the nearest galaxy. Think about this for a minute. You're looking at the screen. It takes very little, but a known amount of time for the light to go from the screen to your eyeball. You are looking a few, probably microseconds or femto or just tiny amount of time in the past just by looking at your own hand or the screen or across the room. That really shows up in astronomy because the distances are so insane. Have a good day.